Hello, hello. This is Pius from Pius Labs, and I am going to give a very broad tutorial on how to program lots of LEDs onto an electronic textile. So very recently, I had the opportunity to explain to a visitor what I made about 5 years ago, and you can see it right here. I made this thing. Let's bring our little screenwriting tool over here to make it easier. I made this thing. It's an electronic quilt, and it's been so long since I made it that I was starting to forget what I did, and it was really hard to explain to her, hey, I connected this thing to this and that thing to that. And so I decided, well, let's make a little tutorial, not only for other people, but for myself, to remind myself, hey, this is how I made this electronic textile. So what are we even talking about? Well, first, let me just summarize what I just said. I am explaining how to program multiplexing, a multiplexing algorithm to light up a whole bunch of LEDs into some kind of networked electronic system, specifically into fabric. And I'm using the Arduino Lilypad. Some of you might be familiar with it. And it's kind of a cool little microcontroller. Again, this is me on Twitter, and if you want to learn more about all this, you can just, look me up on Twitter, etc. So anyway, that's what this tutorial is going to be about. Thanks for sticking with it. An electronic textile is any kind of electronics that are embedded into fabric. So this is the Arduino Lilypad right there, and this is my fabric. And 5 years ago in 2016, I spent a lot of hours, many hours. This is me, slaving away, making this thing and having fun. I should make that a smiley face. Having fun making this thing. I didn't know how to use a sewing machine before this, but I did know how to solder. Turns out I didn't really have to solder much. And anyway, I sewed in a bunch of shiny LEDs into this quilt. By the way, this whole thing is like 5 feet long approximately by, I guess, 4 feet, something like that. So it's pretty big. That's why it took so long. And you've got cotton and polyester, quilting and lining, and it represents this pattern that I designed. It's got a little lion figure here. It's powered by a AAA battery. And so let's look at some details. So here is a picture of the electronic quilt, my example quilt, lighting up in the dark. The brightness of the LEDs is actually corresponding to the brightness of the actual stars in the Leo constellation. Here's that video again that I was showing right at the start. So you can see it in action. It's not just me photoshopping lights in there. You can see the system LEDs over here for the microcontroller, for that Lilypad. And so the lights went back on in this room, and now you can see the whole thing. So that is an example of an electronic quilt, which is another example of electronic textiles or E-Textiles in general. And once again, if you want to know more about it, you can just look up all the stuff that I've got about Pius Labs. You can even check out other cool stuff from my studio, Pius Labs, by going to the website, piuslabs.com. If you like what I do, please support me on Patreon. It's totally helpful when people donate to these projects of mine. If you're an educator and you want to find curriculum guides for random things, I actually do a lot of math these days because I'm teaching math. You can find some of my stuff that I've made over there. And then, of course, all the horrible social medias that are taking over the world, I'm there as well. Anyway, back to this tutorial and how to make an E-Textile of your own. So this video is all about walking through my specific example quilt. And that means that it looks like this, and to explain how to do what I did, I got to give you a bunch of background. I pointed out some of that background. Well, let's just zoom in on this thing. That's like my control patch. That's what I'm calling it, because it's actually removable. I had thought back in 2016 that what if I want to clean this in the washing machine or in the bathtub? Well, if so, you don't want to put this computer and this battery pack in the washing machine. That's bad. Electronics and water and soap don't mix. So I made it removable. Here's a close-up view on that. And like I had said, we've got our Arduino Lilypad sewn right into this denim here using special threads and stuff. And we've got, you know, our battery holder right there as well. Let's talk about the Arduino Lilypad, our computer or our microcontroller that controls the lights. So here's a picture. This came from SparkFun. SparkFun is a great source for electronic hobbyist stuff like the Arduino Lilypad. I happen to get my first Arduino Lilypads from SparkFun, but they aren't paying me, don't worry. But you can SparkFun if you want to donate to me. And it's a great little PCB. It's a great electronic device. This specifically is the Arduino CPU, if I understand correctly, I think. And it's wired into all these different channels coming out like a flower. So for example, it's connected to, you know, analog 1 or analog 2, analog 3. You've got all these other digital inputs and outputs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 13. You've got a reset button, and you've got your input power, you know, your negative terminal and positive terminal right there. So all of those terminals, all of those channels are important in this microcontroller, this computer here. And we hook it up to a battery pack like I showed you earlier. You hook up negative to negative, you know. Maybe we should make it black just to like follow the standards of some American electronics. And then we do positive to positive. And in goes our AAA battery right here. You can just pop it right in. Make sure you put it in the right way. And if you flip the thing on, it's got a little on button, the power will flow. And all of a sudden, it's like plugging in your computer. The computer or phone that you're using to watch this video, well, that has power. And this little Arduino thing has power as well. So we're going to connect it with wires. What kind of wires are we going to use? Oh, there's my Energizer battery. But what kind of wires are we going to use? Are we going to use these stranded or solid core wires with plastic insulation, the same kind you would find in your computer? No, we are not. Why? Because this is too stiff. It's too big. We're going to use thinner conductive thread. Wonderful stuff. And this image came from Adafruit. Thank you, Adafruit from New York City. I got this from Adafruit. This is actually what I learned is this whole thing is called this holder is called a bobbin, and over in here you've got your conductive thread wound around your bobbin. And if you have conductive thread wound around a bobbin, you can actually put this thing in a sewing machine, and sewing in your conductive wires here, your conductive thread, becomes so much faster. So learn how to sew if you're ever going to do this with a machine. It's so awesome. And in fact, you can even use programmable sewing machines, I found out, and you can go to like a makerspace and rent it out for a lot of money, or just buy one for thousands of dollars and program it like a CNC. Anyway, that's for another day. I'm just saying use this thread to make those connections. The LEDs that we're going to use, the ones that I used, they look like this. They come in, you know, connected to each other, but you break them up. They're like pieces of chocolate, right? You can break off an individual one. So this little guy has a negative terminal and a positive terminal. And LEDs, you may recall, they only work if you power a bigger voltage over here, so you might use a symbol V plus for that, and a lower voltage over here, so maybe you'll put V minus over there. Or you might even just say, hey, let's just ground that negative side and put our hot voltage, our high voltage over here. So maybe V high or some symbol like that. Specifically, I think the ones over here operate at either 3 volts or 5 volts, something like that. I'll put a question mark. And so you would ground it like that over there to power these guys. And I'm going to sew those, or you're going to sew those directly into your fabric. Once you've got all your equipment, or you know what the equipment is that you have available, you can make your design. Well, this is a picture of how you might sew in your LEDs. And this is actually a picture that I took of my design. It's going right into the cotton. And I use my conductive thread there. And my cotton thread is kind of an insulator. So you might play with using your fabric materials as insulators and using your thread as your conductors. In any case, you lay it out according to whatever design that you want. If you just want to have a single light on your entire fabric, I don't know why you would want something so boring, but let's say you just want your single light. Okay, this is me sketching it out, and it's got your positive terminal and your negative terminal. And if you wire it up correctly, it will light up. Well, you would have to connect, you could connect it, I should say, to 2 channels on your microcontroller, on your Lilypad Arduino. For example, like this. And for example, channel 13 over here is connected to my positive terminal of my LED. 12 is connected to my negative terminal. And in the Lilypad Arduino, you just use Arduino code to program this computer over here to make this channel 13, you're going to make it high. And you're going to make this channel over here, you're going to make 12 low. That's like a shorthand way of saying it's like 5 volts. I think it's 5 volts. Again, I'm kind of making it up. This is how long it's been. I don't know. But it's either 3 to 5 volts, so that's high. And low just means this is basically 0 volts. And when you have that drop in voltage between your positive and your negative, this thing will shine. Yay. So my point is, if you want to make one LED shine like that, you probably are going to use, in its most basic form, you're probably going to use 2 channels. So, hey, this is my design. Maybe that's all I want. Okay? Then you're done. Put it in your jeans and you're cool. The thing is, I don't want to just program one single LED. I want to program several LEDs. Specifically, in the example I showed, I wanted to sew in LEDs according to the Leo constellation. I'm not an astrology person. I just like stars. And so this was my design pattern. And in fact, I wanted to have Regulus, this star, be the brightest one. So whatever LED represents Regulus, I wanted it to be the brightest one. Likewise for Deneb or Denebola and these other stars, I wanted them to have brightness, or I wanted the LEDs to have brightness according to the stars you would see in the sky. So how many stars was I going to put in my example? 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe, maybe more. There's actually more stars that you can consider as part of this constellation. Go and read your history about Western constellations, I guess. And I ended up deciding to choose, I think, 16 stars. 16 stars to represent with LEDs on my blanket. And I then matched up in my design, where was I going to place those LEDs? I was going to put one there, one there, one there, one there, one there. Here I am redrawing my constellation roughly. And I put it actually in some CAD software so that I had a record of like where everything was going to go. I measured out the distances between all these stars so that it was kind of accurate. But my problem was exactly what I'm saying here. How many channels did I need? How many channels did I need to use on the Arduino to light up 16 of these guys? Because I just showed you that previously, if this is my LED, and by the way, here's the electrical symbol for an LED. You put your positive voltage there, your negative voltage there. Well, if I want to light up this single LED, I just told you how you're probably going to use, one channel over there to make it high and one channel over here to make it low. 2 channels per LED? So do I need 32 channels? Do I need that? I don't know. So let's think it through. If I tried powering all 16 LEDs using 2 channels each, what would that be? So I'd have it like connected like that. I'd have another one connected like that. I'm using my electrical symbols here, fancy me. And another one like that. And you might already be able to predict what's happening. will I be able to light up all my LEDs? 1, 2, 3, 4, 5, 6. Oh, and I even cheated, by the way. You can't, oops, I already messed this up. So this is, I can't use the power channel. Like, so let's just remember, there's a battery going in there, okay? What's a symbol for a battery? Let's just use this. There's a voltage going in here, negative and plus. That's our power. You can't use that for LEDs. So really, this should be like going all the way to this channel. So I'm so far powering 1, 2, 3, 4, 5. We're going to get a 6th LED over here. We're going to get a 7th LED if I use my analog channels, because that's what A stands for. If I use my analog channels as digital outputs, then I can power some more. And so I've got 7, I've got 8. I think I can maybe do one more. I can power a 9th LED. So I can do 9 LEDs, I think, in the simple way. And I think this is like a communication channel, and I think I can possibly use these two. So I don't know, maybe 10? Maybe you can do 10? This is for you to research. But I have a problem. I could not light up all the stars that I wanted to in my blanket using this simple wiring pattern with 2 channels per LED. So what if we could do something else? I thought about, well, could we power many groups of LEDs in parallel using just 2 channels? So let's just say I use channel 13 and 12, right? This is my high voltage, this is my low voltage, and I'm like, let's just power one of them over here, but let's just power a second one in parallel like that. And if you remember in grade school trying to light up little lights in parallel with a potato or something, this might look familiar. So I could keep on sketching this out, and I could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I could try to do 16 LEDs in parallel. Well, okay, then I have enough channels in theory, but there's a problem again. Each one of these channels has a limited amount of current, limited amount of charge that it can spew out per unit time. Basically, there's not enough juice that can go in and power all of these LEDs at once. It's kind of like releasing water into your garden hose, except your garden hose is splitting off into 16 lines. Maybe you could do a couple of them, but not 16. So that's a problem. Also, all I can do is turn them all on at the same time, right? This is on, this is on, this is on, this is on, this is on. If I make this high and this low, and I can only turn them all off at the same time if I make, this thing suddenly go low as well. Because if I make this low and this low, there's no voltage difference, so these would all turn off, I can't control each LED individually. They all have to be the exact same status. That's kind of dumb. So we've got limited current, and then we've got, I'll just call it really dumb control. Really broad, like I don't really have control. I just make everything do exactly the same thing. That's stupid. That's not how the stars are. So this is a problem as well. Not going to work. Instead, we're going to try to use multiplexing. You can Google it, but maybe you're watching this video to learn more about this. Just make a note. Multiplexing is not the best or the only way necessarily to handle this. There's apparently something called Charlieplexing, if I'm spelling it correctly, which I looked into, but it's kind of more complicated to program, or at least I just don't know how to do it. There might be libraries that help you do it, but anyway, just note that, yeah, we're doing multiplexing here in this video, but you could look up Charlieplexing as well. That said, you can precisely control each of your 16 LEDs separately, and you don't have to use a lot of channels. You can use 8 channels if you want for multiplexing. Let's talk about how. So this is a rough CAD sketch of how I connected my wires, how I connected my electronics to each of my 16 LEDs. I don't want to get into too much detail about this specific pattern just because it's kind of complicated to look at. Instead, I'm going to use as this example in this video of a simpler case. So let's start out by wiring stuff to our Arduino Lilypad, our Lilypad Arduino. And we're going to talk about powering 16 LEDs. And the way we're going to do this is first we're going to connect some channels, specifically 4 channels, to some of our LEDs, okay, or to all of our LEDs. These 4 channels are all going to be positively powered, or they're going to be set on high. So we can make these channels go to their high voltage, basically. They're 5 volts. That's why they're red. They're hot. You can consider them hot. Kind of like you've got a hot terminal in the plugs in your wall in your house. But this is way less power. And then the other thing we're going to do is we're going to make some of our terminals connect or only provide the ground or the negative voltage. So these black channels here, these ones connected here, they're all going to be set to low, or basically 0 volts, or ground, GND. It makes me think that if you study electronics, we have all these different symbols and abbreviations and words for the same thing, I guess. So in any case, these 4 are responsible for our low voltage, or they're going to be connected to the negative terminal of our LEDs. And so what I mean by that is we're going to connect our LEDs like this. Here is our here's our diagram of our LED symbols. So this is the symbol for an LED. Once again, it's shining. That's what those arrows are. And LEDs only work if you connect them in a certain direction. They have a polarity. It matters what direction you connect them in. That's what I was saying earlier. You want positive on this side and negative on this side. That way, your charge, your voltage goes high and it comes down low, and it can travel through this wire down to this other channel, and I can power that one right there. I should also note that these black wires, they look like they're crossing on this image because it's a 2-dimensional image, but these black wires do not electrically touch these red wires. Specifically, it's like a sandwich. It's like the red wires are on the bottom of the sandwich, and then we've got some cotton on top of all of this because it's a fabric, right? And then on top of the cotton, on the very top of our sandwich, we lay these black wires. So there's actually a separation between the red and the black wires. And the only thing bridging these red or hot wires to the ground or black wires are these LEDs. And just to repeat one more time, you can look at any LED, and how is it going to light up? It's going to light up because it's powered by one channel. In this case over here, it's providing our high voltage. And over here, it's grounded all the way back into this channel over here. That's got our ground or our negative voltage. If you provide a high voltage here and a low voltage there, we're going to properly power that thing. You're putting the polarity in the correct direction, or it's the voltage has the correct polarity. You might say it's forward biased. All you electrical engineers and stuff might know about this, but if you provide the voltage in the proper way, where this is high and this is low, you would say it's forward biased, and it's good because now it's shining. And if you look at any one of these LEDs, notice that they are all connected to a hot voltage and a low voltage, a high voltage and a low voltage, in theory. So if these are all set to high, if you set your Arduino to make this channel high and this channel high and this channel high and this channel high and this channel low, this channel low, this channel low, this channel low, these will all light up like Christmas time. So I'm just summarizing what we just said, they're all lit up. And you can actually get other patterns besides having everything on or off. You can turn everything off. How? How? Well, you could leave all these low. You know, all of these could just stay low. And then you could turn these to low. Then there's no voltage drop. There's no voltage difference. And these will all be off. You need a voltage drop from in this direction for it to turn on. You could also make them off or keep them off if all of these channels were low and all of these channels were high. If this is what you do, then you would call this reverse biased. It's kind of backwards from what you would expect. Because now you've got a high voltage here and a lower voltage here. Meh, not going to work. Your lights are going to be off. Okay, it's reverse bias. Not only there is a voltage difference, I guess now, but it's the wrong direction. It's like the wrong polarity. So anyway, you can turn all these LEDs off if you do a reverse bias, or you just make sure there's no difference in the voltage. So in fact, you could make these high, and you can make these high as well, and these will all still be off too. You have 3 different ways to make all these LEDs turn off, and 1 way to turn them on. So then the question is, how do you make more complex patterns? Well, you could turn on a single row. How? Think about that. Maybe you turn this high, and you make all of these low, okay? Because now that's proper, right? You make that's positive to negative, that's good, it lights up. Positive to negative, that's good, it lights up. That's hot, that's grounded, great, lights up. Hot and grounded, great, lights up. But what do you do to these other channels to turn these off? Well, we said that we can make these turn off if there's 0 voltage drop or if there's a reverse bias. It's already low down here, so let's make this low. Let's make this low, let's make this low. That means there's 0 voltage drop across all of these LEDs. None of them will turn on. So that's an example of turning on a single row. You could turn on a single column very similarly. So for example, I want to light up this entire column. So let's make sure that this is low. Okay, we're going to set this channel low, A3. And I think we got to turn all of these to high. Each one of those have to be hot. That's how these are all going to turn on. But I need to make sure these are all off. So if this is high over here, the only way we're going to turn this off is if this is high as well. So I'm going to go ahead and turn this to high. We're going to turn all of these to high. And that'll turn off all of these because now there's 0 voltage drop across these. Let's talk about one more case. What about turning on a single LED in one specific position? Practice that one. And maybe you already thought about it. Maybe this is easy. Maybe you can skip ahead, but I'm going to think about it. I know that all of these are off, so maybe... Well, okay, let's focus on the one that's turned on. I know that this one over here, because there's only one way to turn it on, we have to make that low, channel 11. And this channel, channel A1, that has to be high. Logically, that's our only way to do it. So I'm going to first think about how do we turn that one on? And it's like Sudoku. Okay, what do we do to the other ones to make sure they're all off? So let's see. This is low. So maybe I can turn this to low because that'll turn that off. This is going to be low. So that'll turn that off. And low, low. This can be low because that way there's 0 voltage drop there and that'll turn that off. Next, we got to think about this column here. So this is low. Maybe we just turn this low. Now there's 0 voltage drop. Same thing for this one. Turn this low. Same thing for that one. Turn that low. Okay, that's one way to do it. Now everything should be off except for the single LED that I wanted. Okay, finally, how do you make a more complex pattern? If you try to troubleshoot this one, it's a little difficult using the same methods that I just showed you. And let's just work through one of them. just to try it. So for example, I want to light up this first LED here. Well, we know we've got to make sure the it's forward biased. So I think that channel A1 is going to be high, if you agree with me on that, because we got to make it positive, negative. So it's going to be high over here, and this is going to be low over here, and I guess this one's going to be low over here because we want to light up this one. So this is taken care of, that's taken care of. And let's see, if that's low, we want to light up all these other ones. So I'll change that to high. So that's lit up, that's lit up. And so now I got to light up this one. So I'm going to change this to low. So that's lit up. And then finally, I need to light up this one. So the only way that's going to work is if this is low and this is high. But uh-oh, look at what happened. Now we should check all these ones that are supposed to be off. What's happening over here? High, low. This is on. Uh-oh, that's not what we wanted. Not only that, this is on. That's not what we want. This is on. That's not... Okay, so clearly these are all going to be turning on. That is not what we wanted. So warning, warning. When you want to light up more complex patterns like this green pattern shown here, we start to run into difficulties. You can light up a whole column. You can light up a whole row. You can light up a single LED. But lighting up more complex patterns simultaneously is a bit more complicated. So how are we going to do this? We're going to use multiplexing. Multiplexing says that we're going to trick our eyes and our brain to see this more complex pattern. We're going to trick our eyes and brain to see that more complex pattern. We aren't actually going to display this pattern all at once. So our Arduino Lilypad is going to do something a little more complex. We're going to say, let's just focus on one column at a time, for example. Let's focus on one column at a time. Let's focus on one piece of the pattern that we definitely can do. So we're going to think about, well, how can we light up just that desired pattern, that first column? And we know how to do this. Let's ignore these other columns. We're going to turn those other columns, let's use black, that makes more sense. We're going to turn all of these on low because we're ignoring them, right? And the only thing I care about is this first column. We're going to set this to low. We're going to set this to low, this to low. That way all of these are off, 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 and off. And we're going to set, oh, I got to put that one to low as well. We got to turn this one to high. So in the Arduino, we can make this columns pattern just like that. And then a couple milliseconds later, we're going to make this pattern. We're going to make the next desired pattern. We're going to look at the next column and do that one. So we're going to go ahead and ignore those other columns. Oh, wait, you know what? I think I might have messed up something. Let's go backward. I think I might have misled you here. Let's go back and let's go back and do this one. I think I screwed that one up. The surefire way to ignore these columns actually is to make all of these high. We're going to reverse bias these columns that we aren't even interested in. Okay, we're going to do just this pattern for a couple milliseconds, few milliseconds. And now we're going to do what I had said. We're going to make this low. We're going to make this low, this high, this low, and this low. Then that's kind of like a surefire way of turning off all of these. Because the way I showed it previously, you might have noticed my mistake. I believe that would have, if you didn't make this high, you would have had a voltage drop across these, and that would have messed up. So the key is actually we're going to reverse bias the columns that we want to ignore. Okay, that said, let's do the next column. So in our code, we would focus on next for another few milliseconds. We're going to light up just that, and then we're going to go ahead and reverse bias these things by, making sure that these can't light up at all. There's no way. And we're going to set this column to low down here, and we're going to light up this one, set this to low, set this to low, set this to low. And you'll notice now the way I've got it, when this is high and this is high, there's 0 voltage drop. When this is low over here and this is low over here, that's off. When this is high here and this is low here, that's on. And let's test it out. Let's look at this one here. It's low and it's high over here. So it's reverse biased here. So that's going to stay off. Everything else is as it should be. Okay, next step. Let's do the next column. This is what multiplexing is. You program the next little thing to the next column to light up properly. And that means, like we said, what are we going to do? We're going to make this high. We're going to make our, so that gets rid of that one. We don't have to worry about it. We'll make that high. We'll make that high. It sounds like drugs, but it's not. We're going to make this one low because we want to be able to control this one. You got to ground this column if you want to light it up. And we know that if that's low, we want to make that low to keep that off. But these other ones are all going to be high. And when you're high on this and you're grounded, when you're both high and grounded, you're going to shine. I wonder if there's poetry related to that. Okay, finally, let's just hurry this up. We're going to do the last pattern. Similarly, you would reverse bias all these things. I'll just set all 3 of those channels to high, and we're going to set this channel to low. We got to ground it. We're going to set these all to low because we don't want to turn them on, and this one over here is going to be high. It's like Sudoku for multiplexing. All right, anyway, if you can do that logic, you can do multiplexing. The point is that each time you made that pattern, column by column, a few milliseconds passed by. And if you cycle that pattern over and over, right, like going like back and forth, well, probably not back and forth like this, I'm just flipping between slides, but you can imagine if you repeated that pattern over and over, do it fast enough, and you do trick your eyes and your brain to see this. Even though, my Arduino is being very crafty, right? They're being crafty by blinking really fast. It's actually blinking, but our eyes and our brain don't perceive that blinking. We just see a nice, smooth pattern. As long as you do it fast enough. If you cycle through these columns and these patterns fast enough, it's very smooth. A key that I've italicized here is, though, you sacrifice some brightness. You're not leaving this LED, for example, on the whole time. It's really like flipping it on and off, like really fast. And so because it's off some of the time, it's not as bright as it could be if you just left it on the whole time. It's kind of like if you walk into the room and you flip on the light and then you flip it off and you flip it on again real fast. Yeah, do it fast enough and you can't even tell the difference. Okay, so that lets you, this multiplexing strategy, cycling through columns or whatever, that lets you create more complex lighting patterns like this. But wait, that's still a static pattern. How do you make your multiplexing a little fancier? How do you get something like this? How do you get closer? Notice how sometimes we're turning off the LEDs. Sometimes we're turning them on. They're getting dimmer. They're getting brighter. We got to have more dynamic patterns here. Otherwise, it's kind of dumb. So how are we going to do that? We're going to use pulse width modulation. Okay, we're going to program PWM into your code. This is something that you can look up more about if you want, but we'll give you a quick tutorial on that. We're going to control the average brightness that your eyes see for an LED using PWM. And the concept is just what we just said before. It's that idea where let's imagine that for a single LED, you input maybe 0 volts for a little while to power it up, and then all of a sudden you give it the full high voltage, right? Like basically when you're looking at your LED and you're connecting it to your positive and your negative terminals, we're basically saying your input voltage is going in here on your positive side. But you're basically saying that with PWM, you provide no power, then you provide full power for a little while. Then you turn it off, you provide no power. Then you turn it back on, and you turn it back off. Turn it back on, turn it back off. This is pulse width modulation. That's what the modulation part of this means. Modulation is you're varying the amount of input power into your LED. What that means on the Arduino Lilypad is that your channel is going to be flipping on and off. The cool thing is that for the Arduino, you can turn your inputs high and low whenever you want. And so this is the pattern that we're going for, and let's see if we can zoom in on one of these cycles. Let's say from the start of a cycle is right there when your power is on, and the end of the cycle is right there when the next, like it's after you turn it off and it's the next time you turn it back on again. This is one PWM cycle. That's one PWM cycle, and that's what we're going to zoom in on. If we zoom in on one PWM cycle, let's make a new little graph, we talk about one pulse or one cycle as having, or you can measure its duty cycle of one of these pulses. So let's say your pulse, it starts out high, you know, and it turns off, you know, right there. And then after a while, it turns right back on. Okay, so this is one full pulse. This is one full cycle, the thing that we zoomed in on. The way I sketched it, it looks like it was on for maybe 50% of the time, right? Because this is basically like time, right? And at 0% of the cycle is over here, 50% of the cycle is over here, 100% of the cycle is over here. And it looks like, you know, our pulse, our power is on 50% of the time. So for this pulse pattern, we would say it's got a 50% duty cycle. It's basically saying your light is on half the time. And you would say that maybe it's half as bright as if it was on the whole time. Because a pattern, let's talk about that pattern of if you never turn it off, then you've got full power the whole time. That's a 100% duty cycle. The 50% duty cycle is half as bright. And you can program different duty cycles. You could have like a 10% duty cycle where it's on for just 10% of the time in one pulse. And it's off the rest of the time. This is going to be even darker. This is like the pulse pattern for a 10% duty cycle. And so if you program your LEDs with specific patterns, you can make your LEDs darker or lighter. So going back to that long time cycle pattern that I was talking about earlier, a really bright LED might be on for a lot, then off, then on for a lot of time, then off, then on for a lot of time, then off, right? Whereas a really dark LED, a really dim LED might be on for just a tiny bit, then off. Then on for just a tiny bit, then off. You know, that's a low duty cycle. Maybe that's that 10% duty cycle. On for a tiny bit, then off. It's mostly off. The power, you know, you're getting your high input power for just a little bit of the time. All right, so that's duty cycle. You can look up more about it if you need to. I had to talk about it because eventually we're going to program the duty cycles or the PWM pattern for all 16 of our LEDs, all the LEDs of interest. And that way they're not all at the same brightness level. You can make some dim, you can make some bright. So like I said, maybe LED 1, maybe this is Regulus. My brightest star, remember that? It's going to be real bright, so it's on most of the time, right? maybe it's got like a really high duty cycle, and then you've got a really dim star, one of those stars that I don't know the names of. It's going to be mostly off. It's got a certain low brightness. Okay, and there's going to be a duty cycle pattern for each one of my stars or each one of my LEDs, whatever it is. And that's based on, you know, my design decisions, et cetera, et cetera. I'm not going to draw all 16 of these. But the point is that maybe for LED 1, it's going to have a duty cycle of 50%. LED 2, it's going to just, the power is only going to be on 10% of the time in one cycle. For LED 3, it's going to be on 23% of the time in one cycle. And you just have to make those decisions or figure out, maybe this one's off. I don't know why you would do that, but this one could be off the whole time. And maybe this one's on the whole time. And you decide, okay, what's the duty cycle for each one of these LEDs? That will get you a certain brightness or dimness level. And this is just in the diagram kind of explaining that, like right here, maybe this is an LED that's on all the time. So it's got the maximum duty cycle. And so, I don't know, it's got a really, I'll just say large duty cycle. And then you've got this really dim one over here, which is a really small duty cycle. The power is on just for a little bit, right? This channel here, for this guy, we're going to turn on the power just for a little bit. And if you go like column by column, you can program that into each LED. All right. But wait, the problem is that's still static. I only told you how to have a constant brightness level. What about for what I just showed you? Here, the brightness levels are changing. Some are getting dimmer, some are getting brighter. So it's not just that Regulus down there is the brightest, it's that the other ones will pulse in and out like a real star. So how do you get varying brightnesses? Okay, this is where you got to take into account the long cycle. So over a long period of time, you're going to have some way of figuring out the brightness that you want your LED to be. So for example, I might make the decision, I think I did make the decision, that between 0 seconds and 10 seconds, the brightness of Regulus, my LED at Regulus's position, was going to be relatively bright. It starts out pretty bright. Like if this is my max brightness, whatever number is going to represent that, it starts pretty close to that, and it goes high, and then it goes down, and I make it pulse kind of like that. And then for one of those no-name stars that I don't care about, I might make it off, and then it turns on to like half brightness, and then it goes back low. And I make it kind of, you know, follow some sinusoidal brightness pattern. I have to make that decision over a long period of time what the brightness level is for those LEDs. And then once I've made that decision for all 16 of my LEDs, these are just 2 of them, right? This is star, oops, that's way too huge. Let's clear that. This is just star number 1, and this is just star number 2. I have 16 stars to decide what their brightnesses are over the long cycle. Once I've made those choices, then I've got to go and say, okay, at each point in time, let's say at every half second, right? So at 0.5 seconds, what is the brightness of star 2? What is the brightness of star 1? You know, maybe that's a brightness of, so if this is a max brightness of 1, then maybe this is a brightness of 0.9, and this is a brightness of 0.08 or something. And then I have a value for the brightness for all 16 of my LEDs at this particular point in time. If you're a math person, you might say that brightness is a function of time. So brightness is equal to a function of time. And that's actually how I thought about it. I'm not going to go into the details here, but I made, you know, a sinusoidal curve to represent the brightness where, you know, I knew what the range of that sinusoid was, and I used like I don't know, I said that brightness is equal to, and I'm totally making this up, but it's something like 0.5, whatever your amplitude is, times cosine, some frequency times time, plus some kind of shift, you know? So you have to look up your trigonometry, look up your math, basically, if you want to make these kinds of curves. Essentially, you need some mathematical function relating time to your brightness, the way I've got it here. That way, at any point in time, you can get the brightness of any LED. And now, time to get to the code. The reason why I explained all of this is I want you to understand that there are nested loops in my example software. There may be better ways of programming this. I'm almost sure there are, but I just want you to think about how the code that I'm providing works. The long cycle in my code is exactly what I just spoke about. Maybe it's 10 seconds. I think I tried different ranges, maybe 5 to 10 seconds. And this is like the cycle that we see with our human eyes, that a star could be getting, you know, it's dim and then it gets real bright at 5 seconds and then it gets dark again at 7 seconds and then it gets bright again. That's the long cycle that we can feel and sense as humans easily. It's also kind of the overarching loop in our algorithm, in our code, as we'll see later. Another important time cycle is the pulse width modulation cycle. So I just said that for a particular LED, you have this long cycle of brightness versus time, right? If this is your brightness and this is time, well, at some specific point in time, you know, or, sorry, let me rephrase that. I can break up this long cycle. I break it up into a lot of little PWM cycles. You can imagine it as like slicing it up with scissors. And it's literally just a tiny fraction of a second. I said hundreds of microseconds, so maybe, I'm just making it up, maybe it's like 500 microseconds. And we can check the code later, what I said, but you can also change it and play around with it. This is my PWM cycle. Okay? That's how long the PWM cycle is. And in that PWM cycle, we're like, okay, what's the brightness supposed to be? I know that it's a function of my time, right? If we know what the brightness is during a PWM cycle, we can figure out the duty cycle. We can figure out what is that pulse going to look like. So within within this like 500 millisecond window, or microsecond window, I should say, I'm thinking, well, what's my duty cycle going to look like? Is it going to be like that? You know, where it's only on for a shorter period? Or is it going to be on for like a really long period in my duty cycle? That's the decision we got to make for each of these PWM cycles, for each LED. And then finally, imagine that you've got your pulse pattern, right? Here's my pulse. And in this particular case, it looks like it's got, I don't know, 70% duty cycle. Well, we got to break down this PWM pulse, or this pulse cycle as well. Imagine cutting this up into a bunch of little pieces too. I think the way I programmed it in the code we're going to see is I broke up one pulse into 100 little segments, and I'm calling them PWM segments. There's 100 of them in here, okay? And so those are just a couple of microseconds. If this whole pulse was 500 microseconds and I had 100 segments, then that means one little segment that I broke this up into was just 5 microseconds, really tiny. And the reason why we break up a pulse into little tiny segments is at every single segment we ask this question in our code. We're like, again, here's our pulse. We're like, okay, go move one time segment forward. Do we turn off the LED? And I'm like, no. Okay, move another segment over. Do we turn off the LED? No, it's supposed to be high, so go another segment over. Do we turn off the LED? No. Do another segment. Do we turn off the LED? No. And then finally, you finally get to some time segment where you ask the question, do we turn the LED on or off? Do we turn it off? And we're like, yes, right there. And so in each one of these little segments, we're asking the question, do we turn the LED on or off? And we wait a little bit. So if it's on, you're going to wait and let it stay on. You want some time to pass before you ask the next question, right, of whether or not you have to turn the light on or off. Okay, so those are the time cycles that you have to understand are important when programming this multiplexing algorithm. Also know that we're going to use nested loops in our algorithm based on those cycles. The code that I'm about to show you is represented with these loops. I know this is not the most clear example, but let's just go through it. The code itself has a long overarching cycle. It's like the parent loop. And if you're familiar with the Arduino, it's like that overall repeating loop that the program runs on. And we're keeping track of seconds at that stage. Within that loop, we actually look at the lights column by column. Why? Because I said earlier, it's easy to program this when you go column by column. And we said we had 3 columns, correct? 1, 2, 3. So we're like saying, okay, just light up this column, this first column, and kind of ignore these other columns for now. We go through it for the first column. And let's say we're looking at just that first column. Now we start the PWM cycle. There's a loop just controlling the pulse width modulation where we analyze the, well, by the way, you don't have to nest the loops in the order that I have, but that's just how my code is. Within that pulse width modulation cycle, we start looking at each row. So I look at this first row, for example, look at that LED, and I determine, hey, what's the brightness? What's the brightness supposed to be? Which determines, hey, what's the duty cycle? Which also determines when do we turn off the LED. By default, we're always going to turn on the LED at the start of the pulse, okay? We're always going to turn it on at the start of the pulse. It starts out high, powering a single, this LED over here starts out high. And it looks at that row and is like, okay, do we turn it off? No, then we leave it on. Then we go to the next row and look at that next LED. Similar thing. What's the brightness supposed to be? What's the duty cycle? Do we turn it off? No. Go to the next LED. And we go ask that question again. Do we turn the LED on or off? No. Once you're done with all 3 of these rows, you go through the next PWM cycle time segment. So we know that we're supposed to have this PWM pattern here, right? And we only went through this little time segment. So we go to the next time segment. Do we turn it off? No, no, no. Well, for this one, it's a no. Let's say we finally get enough time passing where, hey, we're at time segment 50 or whatever. Do we turn it off? Yes, we turn it off. So we tell the Arduino it's to turn this one off at that time, and it turns off. It turns off. I'll turn it black. But maybe the other ones are still on because maybe they have a bigger duty cycle. Finally, it goes through and the PWM cycle goes through every single time segment until we get to the end of that single pulse, that single PWM pulse. And that's when we go out of the column and we basically, let's just create a new little sketch here. That's when we go back and we're going to the next column. So we finished that first column, that's black. Now we're only going to focus on the second column. And we're going to turn off that third column. And it repeats. We go pulse with modulation cycle, look at each row, etc., etc. Essentially what's happening is we're only lighting up one column's pulses at a time. So there is a large chunk of time where the LEDs are off, right? If we're lighting up this column, then the other columns are dead. They're off. So just know we're sacrificing a lot of brightness to do this. Okay, I know there's a lot, but just to summarize again, this is what we're working with. Before I show you the example code, I just have to explain something that's a little bit more complicated. I actually made my physical layout of my wires or of my connections look like this. It wasn't a 4x4 matrix. It was a 3x6 matrix. I had 3 wires connected to the ground. That's what these black wires are here. And I have 6 wires connected to the positive terminals of my LEDs. In theory, I could do 18 LEDs, but I only powered 16 of them. That's fine. You can still control it column by column. And the reason why I did this was, just like I said, whenever you have multiplexing algorithms, you sacrifice brightness. And I said that with a 4x4 design, when one column was on, when this column is on, all the other ones were off. Well, if you had 4 columns, I'd have to light up this 4th column as well. And it just means that the LEDs would have had more off time, If I did just 3 columns, that means that there's more on time. I don't have to cycle through as many columns. Imagine if I had like 100 columns, for example. That means you're lighting up this one column and you have to wait for 99 other columns to be lit up before you can light this one up again. That's why I changed my design to this. And now, if you look at the code that I'm going to explain, this physical pattern explains why I have different channels the way they are. Okay, so next you can go ahead and look at the code, which I've put up on GitHub for anybody to play with. It is totally rough, and you'll see. And so if you visit GitHub, here it is. And just to be clear, the code that I'm going to show you is basically this last one, program 6, star intensities 2. It's after all these other versions that I went through, which may or may not work. You can try it yourself. And yeah, so if you go to program number 6 and look at the code, we can go through it. It's a little bit small here, so let's actually get out of that. And instead, I'm going to show the actual Arduino code directly. So here are just some comments. You can read the comments if you want. Just know that my code is very specific to how I wired up my Arduino. I had certain wires connected to channels 13, 12, 11, 10, 9, and 8. I had certain channels connected to 7, 6, and 5. It looks like I grounded 7, 6, and 5, or these are the ones connected to the negative terminals of the LEDs, and these are the ones connected to the positive terminals of the LEDs. And you can go ahead and look at that yourself. I initialize a whole bunch of variables, okay? But just know that the basic things you got to know are, first, I'm initializing the channels. That's fine. I have some debugging options set up if you want to look at the serial monitor. Oh, right. Okay, so what's happening is I'm initializing the brightness as well, the initial brightness of all of the LEDs. I set the minimum brightnesses for all the LEDs. That's just something that I decided based on the constellation and the brightness of each of the stars. Those are like constants, essentially. And then we set up our pins to be able to write on them, to set them either high or low power. And now we go to our long loop, our overall nested loop. You can ignore the sensor. I actually had a light sensor in this, but the important part here is that first we are determining in this long loop, what is the maximum, or what's the, oh, this is just long patterns, I guess. Like, what's the period of the pattern for each LED? You know, I guess within this long loop, the long cycle, I'm just setting those broad patterns. And oh, here we go. Sorry, this is probably the long loop. I know that the Arduino has this general loop here, but this is where I start programming the that long loop. We start measuring how much time has passed. Okay, we need to know how much time has passed, and then we get into the column loop, actually. Well, I call it row by row, but that's fine. It's just that I'm going through one of my loops. I'm going through the either a column or a row that I'm displaying. Sorry, I'm looking at this again for like the 10th time. It's very complicated. Actually, sorry, I'm just setting the brightness. I'm going through each LED and setting the brightness according to what time it is. So yes, in this long loop, we're checking, hey, what time is it? How bright should each LED be? That's what all of this garbage is. How bright should each LED be? And that's based on, you know, our sinusoidal, trigonometric functions that I was talking about earlier. After you get the brightness, that's where we go column by column. And this is my for loop representing that column loop. And because I said we had, I guess, 3 columns, let's say, well, we're going to turn off all the other columns. We're only going to turn on, or we're only going to ground the column of interest. We're going to set all the other columns to high, or we're going to try to reverse bias the other ones. So all the other ones are going to be off, like we talked about earlier. And then we're going to start the PWM loop, the pulse loop. And within each pulse, we've broken up a pulse into a lot of time segments. I think we set it up into 100 time segments in this one. And that's all the way at the top. Yeah, in this example code, we've got 100 time segments. That was initialized at the very top. And so for the very start of the PWM loop, we're actually going to go row by row, just like I said earlier. If it's at the very beginning, if it's at the very first time segment in our pulse, because we're 0 indexed here, if we're at our very first time segment and there is some brightness, we're going to turn that LED on. And if there's no brightness, we're going to keep it off. And then, however, as we go through, because this is our for loop, as we go through to the next time segments, if we are at a time segment where the brightness level matches the time segment, then we're going to turn off that LED. So for example, the way this code has worked, it's like if the brightness was supposed to be 10 in this pulse, if it was supposed to be like a 10% duty cycle, well, we said that if 10 segments have passed, then we're going to turn off our LED at that exact time. So it's like the downward part of our pulse. That's where we turn it off. And we cycle through all of our time segments in our pulse. And in each time segment, we're going row by row. We're doing it over and over until the entire pulse is done. Here it is, row by row until until the entire pulse is done, until all the time segments in that pulse have passed. After which, we can now go out of that pulse and go back to the next column. We've gone through an entire pulse on that first column before we go on to the next column. So now we go to, as you see here, you go on to the next column. And then in that second column, we go through and activate only that column of interest. Then we start the pulse that we're going to analyze, and then we go row by row, and we just follow that pattern over and over. Turning on our LED when we need to at the beginning of the pulse, turning off our LEDs in that column at exactly the right time. It's kind of key right here that at this particular moment, when the time segment matches the brightness level that we want, that's when we're going to turn off the LED. It's very kind of a key moment in this code. Okay, there's a little time delay just to, let the LED stay on or off for a certain amount of time. And that's it. Eventually, you cycle through everything. You cycle through everything. You cycle through the entire pulse. You cycle through all of the columns. You cycle through the entire long cycle. Okay? Because we basically cycle through this until the loop is done, right? And let me just see where it is. Oh, okay. So basically the loop is only done if enough time has passed. So when the time has passed is greater than whatever our period is. Where did I define that? Here we go. So, okay. So I guess I set a random long period. That long cycle has a random length, I guess. Here I am learning about my code. As you can tell, I've done this a very long time ago. That's why I'm not knowing all the details about what I did here. Shorten the period when brighter aim. Okay, so I made the length of the long cycle dependent on my light sensor, which I didn't really talk about. But when it's brighter, we made it cycle faster. I made the stars basically blink a little faster. And when it's darker, they blink slower to be softer. So anyway, you can go through and check program 6 star intensities number 2 for details about all this, and it is on GitHub. So thanks for checking that out. If you're going to use this code yourself, you have to make sure you wire your channels on your Lilypad Arduino the same way that I did, or you have to adjust your input or your output channels as appropriate. Your pin numbers may not be the same as my pin numbers, so you might have to change these things over here. Okay, that's about it. Thanks for sticking through this long tutorial, which was half for me as well as for you. I hope that you get a chance to create your own E-Textiles. Why? Because E-Textiles are amazing. Thank you so much, and keep checking out my work in the future. Let me know, by the way, if you make something cool. I would like to check that out.